Okay, now we know what the move structure is and sort of what it looks like. It's time to figure out how do we query it. In other words, how do we go through the permutations? How do we execute the permutations that the move structure is representing? So in other words, how do we compute pi of I? Pi is the name we gave to the permutation that we're representing with the move structure, though really, if we want to use it as a full text index, LF is a good example of a specific permutation that we would like this to be able to enable for us. So how do we compute pi of I? And maybe more specifically, how do we compute the kind of repeated pi of i's that we tend to need in practice? In other words, when we LF, we usually LF repeatedly. Maybe we're doing the match query, and so we're LFing from the top and the bottom of a range of rows. Maybe we're doing an extract query, we're extracting part of the text. Maybe we're doing LFs to get to the nearest suffix array sample. No matter what, we're usually doing repeated LFs. So we'd like to be able to do LF followed by LF followed by LF, or pi followed by pi followed by pi. That's what this notation is trying to show. So like pi to the x is composition x times. So like, you know, pi of something. So that would be like pi with 3 in the exponent of I. Okay, so how do we do these permutations? Okay, let's pick a specific example. Let's say we're trying to permute from this position, k equal 10, I equal 2. So k is the offset, and I is the run ID. So this is offset 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is offset 10. And the run we're in is run 2, because this is run 0 here. This is run 1. This is run 2. So we're at run 2. Okay, which means if we look at the move table, we must be in this row, right? The row labeled run 2. So we're in this row. This row is saying this run starts at offset 4. It has length 9. The run head maps through the permutation pi to offset 52. And if we were to go to offset 52, that would be in run ID 13. Okay? So just looking in this row of the move table, the appropriate row of the move table, immediately tells us how we should move through the permutation if we are the run head. Okay, but we're not the run head. We're partway into the run. Right? We're at offset 10. Our run head is at offset 4. In other words, we're at offset 6 with respect to the beginning of the run. So just taking the answer for the run head is not going to be correct. We have to add on how many spaces to the right we are from the run head. Okay, so recall, everything in the run gets mapped as a block through the permutation, right? Everything kind of goes through the permutation in parallel. So if we are 6 positions to the right of the run head, then wherever the run head maps to, we're going to map to 6 positions to the right of that. Okay, so pi of k, for this k, is going to be computed by first of all taking the move table at row I. I'm going to use orange for I. So the move table at row I, so row 2 in this case, row 2, this row, dot, let's get the pi field, right? Pi. Right, so that's the offset to which the run head maps, but then we need to add on how far we are from the run head. And right, so that's going to be k minus, and let's do another use of the table. Okay, running out of room here a little bit. Dot p, right? Okay, so that's saying our new offset after we go through the permutation is going to be the same as our run head's offset plus our offset from the run head. Okay, and in this example, that means that we're going to take 52 plus 6, right? 52, because that's where our run head maps to, plus 6, because we are 6 positions in from the run head. Okay? All right, so if we just look at this picture, this is the parallelogram, this is this is how this entire block is being permuted. And so if we're a few positions, if we're 6 positions to the right of the run head, that means we map to 6 positions to the right of the run head's permutation. Okay, so far so good. So K prime, we might say K prime is 56. In other words, originally K was 10. When we moved through the permutation, we moved to 56. So we know the new K prime. 58, I'm sorry, 58, because it's 52 plus 6. So the new K, the K prime, in other words, is 58. That's the new K. But now we need the new I, right? Because if, after all, if we're going to do this repeatedly, it's not enough to just know what the new K is. We need to know what the new I is, because we need to know which row of the move structure we should use next to iterate this whole process again. So we need to know what's the new I prime. So what might it be? Well, when we moved, we were originally in this row, and this row has a column called xi. This is the Greek letter xi. It can be pronounced different ways. I'm going to say it xi. And it's got a 13 right here because it's saying that when the run head moves through the permutation, if you were to look at where which run, p run, that offset is in, it would be p run 13. It would be the p run with ID 13. I've highlighted that run here. And as you can see, so we might ask ourselves, if we want to know which run this offset is in, might it just be the same one as the run that our run head maps to? In this case, yes, right? So in other words, run ID 13 is the correct run. This is our run head. Our run head is clearly in that run labeled 13. This is where we are. We're 6 positions over. We also map to 13. So in this case, simply taking the xi field of the move table row for the row that we just moved out of, that would be the correct new row. That's the correct new value for I, the I prime. Okay, so in this case, it worked, right? Just taking xi from the move table was correct. Okay, let's look at another case. So new example. Let's say we're trying to permute this time k equal 31, offset 31, which is in run I equal to 7. And I've highlighted run 7 in the table over here. So here we've got run 7 highlighted. So we know what to do first. We can compute our new k prime quite easily. We just have to take the offset that is the permutation of the run head and then add, how far we are in from the run head. So we're at position 31, the run head is at position 25, so I guess we're 6 in from the run head. And pi is 37, so I guess we're going to do 37 plus 6 equals 43. So we, which is to say this position that we're at, is going to map here to this position, 43. Okay, now we need our new, that's the k prime, that's the new k. Now we need our I prime. So let's do what we did before, and let's just take the xi field from the row that we began in. That is 9, right? 9, because the run head is in run ID 9, p run ID 9. However, our offset, 43, is not in that run. As you can see, just by looking at the bit vector around here, this is a run, this is a new run, and this is yet another new run, and we're in this new run, right? We're not in run 9, we're over here. So in this case, simply looking up the xi column from the move structure row was not sufficient because that new row only covered offsets 37 and 38. We're over in offset 43, so we need to keep going, right? We need to get there. So we need to scan, which is to say, okay, so xi took us to row 9, but row 9 wasn't the correct row. Row 9 was too early. Now we need to scan forward until we find the row that contains offset 43. Okay? In this case, that's going to require 2 scans. Okay, so we have to scan until we reach a row containing 43. The first would be, let's just go forward from row 9 to row 10, and we would find that we are in a run that also does not contain offset 43, right? This run actually only contains offset 39, right? That's this guy in here. Okay, so we're still not where we belong. We have to go one more run forward, and now we are in a run that begins at offset 40 and has length 6, and so that clearly does contain offset 43, as we can also see in the picture here. So in this case, we have to scan forward by 2. Sometimes I'll call this a fast forward. It's just a linear scan forward. Okay, so just a brief note. When we jump to the row indicated by the xi column, sometimes we're wrong, and we have to scan in order to find the correct row. But at least we know which way to scan, right? Because when we jump according to the xi column, we're always jumping to the prun ID that corresponds to where the run head maps. We are further to the right than the run head. So we're always going to be to the when we jump, we're either going to already be in the correct run or we're going to be too far to the left and we need to move to the right in order to find the correct run. So it's kind of a good, even though we have this problem that we have to scramble, we have to get to the correct run, at least we know which way to scan. We know that we need to scan to later IDs from the run that we began at. Okay? This is how we do the query, right? We follow what the move structure tells us in terms of following the permutation for the run head. We need to also update what prun we're in, so we follow what the xi column tells us. That's not necessarily correct at first, so we might have to do some linear scanning to get to the correct run. The amount of work that we're doing overall is proportional to the number of linear scan steps we have to take. So if we want to be able to argue this query is fast, in fact, eventually we want to argue that this query is constant time. So yeah, we want to argue that this query is fast. We have to think about whether and how this number of scans we might have to make is bounded. Is it bounded? What can we bound it by? In this example, we had to scan forward by 2. If you look at different examples, right, just pick different offsets and then use the move table to figure out how you would have to move, how you would have to apply the permutation once to get your new k prime and I prime. And you will see that for this particular example, there are some offsets where if you start there, you can get to your destination with no scanning. That was true for the first one we tried. For some offsets, you can get to your destination but with 1 fast forward, and for others, you can get to your destination but with 2 fast forwards. And this second example that we saw was with 2, right? In this particular example, it doesn't get any worse than that, right? So there are actually no offsets that require 3 or more linear scans. So in this particular case, we can bound it by 2, just empirically. Like if we look at every possible permutation, we can see that it's bounded by 2. However, I don't have to change the example too much. Allow me to just take my row, row, row your boat example and replace it with a new example. As you can see, it's kind of mutated, but it's still a little bit like row, row, row your boat. Here's my new Burroughs-Wheeler transform here. And here are my new P and Q bit vectors. Right, my P bit vector is marking the run heads in L, and my Q bit vector is just their images through the permutation. And in this particular example, if I were to try to apply the permutation to this offset all the way over here, I guess that's offset 62, you can see I would end up having to make many scans because I would end up in this run. This run's run head maps here. In other words, the run head is inside this P run, but I'm all the way over here, right? I'm all the way over here. So I need to do several scans to get to the appropriate run. In this example, I need to do 9 of them, and I have a little arrow showing you all 9 of those scans. Okay, so the worst case, it looks kind of bad. And we don't yet have a principle that would let us bound this. And because we can't bound it, we shouldn't feel confident yet that we've accomplished anything like a constant time query. So this is how we will do the queries, but we have more work to do before we can prove to ourselves that they'll be constant time. And as you'll see, this work is also going to involve somewhat modifying the move structure. Hopefully not by much, but we're going to need to somewhat modify the move structure. So that's in the next video.